Okay, so a universal set is where all of our other sets live, and a complement is everything in the universal set that is not in our other set. So if I want the complement of x, I subtract x from u, and that gets this x with a bar over it notation, like we saw in one of the exercises a few minutes ago. And then in order to get a better picture of what this means, we looked at Venn diagrams like this one. And we also did one of these in an exercise a few minutes ago. And well, we have our universal set represented by a box that contains everything. And then inside of the universal set, we have other sets, and we usually represent these by circles or some other shapes. It just depends on your diagram. And what we wanted to do was just work through these. For example, this region 1, it's labeled 1, is everything that's not in x or y. So I took the universal set. I took the universal set and then I subtracted off both x and y. So I take the union of those two and subtract from the universal set. And our notation using the complement bar is like this. So you take the union and put a bar on top. And then we had a few other sets for 2, 3, and 4. So like x minus y, the elements of x that aren't in y would be this one, 2, and so on. And then that's where we stopped last time. And our first new thing today is this gigantic theorem. I don't think I'll be able to fit it on one screen. And if you want to find it in your textbook, it's theorem 1.1.22. Should be somewhere around page 10. Do you have to remember these? Yes. The short answer is yes, you will have to remember these. But most of them you're going to remember just by practicing, and because most of them are similar to the way that numbers work. So you won't have to really work at trying to memorize them. Let's just start at the beginning. Here I have A union B, and then I'm also taking the union of that with C. And what this theorem is telling us is that I can switch the order. I can move the parentheses. So here the parentheses group A and B, and over here they group B and C. So just like in math, like your elementary math, we know that we can add numbers like this, or we could add the 3 and the 4 together first. We can put the parentheses wherever we want them. This is exactly the same thing, but for sets. Okay, and this is called the associative property. You've probably heard this word before. And before I get any further, in the next chapter, chapter 2, we're going to actually prove all of these statements. So in math, a proof is basically an explanation of why something like this would be true. And in chapter 2, we're going to learn how to come up with those kinds of justifications. That's for a little bit later. So I won't be talking about the proof for these today, like I might in a different math class. So once you've actually worked through the proofs, when you've reasoned through this for yourself. I think that'll really help with keeping these in your memory, because you'll have to think about it. Okay, so that's half of it. The other half says that the same thing is good for intersections. So if I have two intersections like this, I can regroup them, move the parentheses. Part B tells me that I can switch the order of things. So if I have A union B, I can also say B union A. So remember, when you're taking the union of two sets, you're looking at the elements in A and B, and all this says is that if you combine them in a different way, if you take the elements of B and then add to it the elements of A, well, you have the same thing. You're just adding both sets together. And the same thing for intersections. You're looking at the elements in both sets, so it doesn't matter which order you write them. And this one is called, you probably remember the commutative property. So back when you were learning arithmetic, you probably remember learning that if you add two numbers, it doesn't matter what order you add them in. Same thing works for sets. Okay, the next property is called the distributive property. And this is another one that should be familiar from algebra. So if you have 2 times x plus 4, then you can distribute the 2 and multiply each thing by 2. So that would be 2x plus 8. And the same thing works for intersections and unions. So if I have an intersection here and a union inside my parentheses, what I can do is intersect A with B and intersect A with C. So since there is a union sign in between B and C, I'll put a union sign here. Just like there was a plus sign between X and 4, and here I keep that plus sign. And just continuing on, here I have an intersection on the outside, a union on the inside of my parentheses. And here they've been written in the opposite order. Union is on the outside, intersection on the inside. And you can see that it works the same way. You take the union of A with B and the union of A with C. And then since we had an intersection in between them inside the parentheses, we'll use that here as well. So the first 3 properties are the big ones. These actually get names, like the associative, commutative, and distributive properties. The rest of them, they're still important, but they're not, let's see. Okay, so they're still important, but not quite as important. Part D, we're taking the union of a set with the empty set. So in case you forgot from last time, the 0 with a slash through it is the empty set. There's nothing in it. So I'm taking a set and I'm adding nothing to it. Taking the union of A with the empty set, you could just get A. Let's see. Okay, something in the chat. Okay, so now we have A intersected. Okay, so we're having some lag issues. Can you hear what I'm saying, or is it kind of impossible? Okay. Goes mute every 20 seconds. Okay. I guess if it happens again, type something in the chat so that I can tell what's going on. So here we have A intersected with the universal set. So the universal set has everything in it, and we're trying to see what's in A and the universal set, and that's all of A. And let's see, part E, we want to combine A with everything not in A. So if you have everything plus, a set plus everything not in the set, well, you get the whole universe. And if you try to see what is in both A and not in A at the same time, you get nothing. Let's see, part F, we're combining A with A. Yeah, I am recording, so hopefully that will be fine later. I'll upload it right after class. Okay, so I'll just continue talking. Hopefully you can hear me. I want to combine A with itself, but everything in A is already there, so nothing happens. And same if I try to intersect A with itself. You just get A. If I add A to everything, well, I already have everything, so I still have the universal set. If I intersect A with nothing, so what is both in A and in the empty set? Well, that can't be anything because nothing is here. Let's see. Part H is a little bit more confusing to say in words, so maybe I'll just let you think through that one. But I should point out I have a set and I'm taking the complement. So A with a single bar is everything that's not in A. And then I'm going to do that again. So I take one complement and then a second complement. So I have A, everything not in A, and then adding another complement gets us back to A. So it's sort of like flipping a switch. Excuse me, I'm just reading the comments here. Okay. J, here we have the the empty set, and we're looking at everything not in the empty set. So everything else is not in the empty set. So that's when we get U. Is H similar to the distributive property? It's not. It's not exactly the distributive property. Um, your textbook gives this a name. It's something like absorption property. And the reason why it's called this is here, you start with the set A, and then you're combining with it a piece of A. So everything in this set is already contained in A because it's an intersection. So you're combining A with a piece of itself, and nothing happens. This piece gets absorbed into A. And the same kind of thing happens over here. You have A, and then you're taking an intersection with a set that already has all of A in it, plus maybe some extra bits. And that also gets absorbed into A. let's see, I think I was talking about J. So the complement of everything, remember the complement is everything not in your set, but everything is already in U. So that means if you want to see what is not in U, you have nothing at all, the empty set. And finally, we come to K. This one also has a name. I should write it down. It's called De Morgan's laws. And this one is a little bit like what happens when you distribute a minus sign. Because you see, inside of my parentheses, I have a union, and on top of it, I've drawn a complement. And in order to like distribute this complement into the parentheses, I put a complement on each of the sets. So A gets a complement and B gets a complement, but I have to flip the direction of the symbol. So my union flips upside down and becomes an intersection. So it's a little bit like distributing a minus sign. And this is the same kind of thing. I have an intersection inside my parentheses, and when I distribute this complement, this bar, it flips my intersection and turns it into a union. So when we start talking about logic in the next section, we're going to get a little bit of a better understanding about what's going on in part K. So in the meantime, read over the list maybe a few times, familiarize yourself with it, because you will need to know these on the homework. Maybe don't try to memorize them quite yet, but make sure you're familiar with them. Now we'll move on to our last page here for the section. And to wrap up, we're going to talk about families of sets again. Remember, a family of sets is the same thing as a set of sets. Just to illustrate one, I can write down an example. Okay. So this is a big set with little sets inside of it. And you can have anything inside of your set. So like this middle one mixes up letters and numbers. Okay, so keeping that in mind, if I have a family of sets, the union of my family is simply the union of all the sets in the family. Okay. So in set builder notation, it would look something like this. The union of S, this is like a union symbol written to the left of my family. So the union of S is the set of X such that little x is an element of uppercase X for some big X in the family. Okay, so that probably makes it more confusing for some of you. Let's look at an example. And I want to look at a bigger family than we've been looking at so far. So this one up here was a tiny little family. And this one is going to have an infinite number of sets in it. So I have inside of my family A1, A2, A3, A4, and so on. And each of these capital A's stands for another set. let me tell you what they are. So AI, so I is going to be the little number you find next to it, is the set of numbers starting, the set of positive integers starting at I. So capital AI is I plus 1, I plus 2, and so on. So let me write down a couple. A1, we start at 1. So that'll be 1, 2, 3, 4, so on. A2, we're going to start at 2 this time. So 2, 3, 4, 5, so on. Okay. So each of these sets inside of your family is a set of numbers. So if you were at A53, it would be the set containing 53, 54, 55, 56, and so on. So now that we have kind of an understanding of what is in our family, I want to look at the union of the family. So what is the union of S? Okay. So in order to find the union of S, I have to take all of these sets in my family and combine all of their elements. So I have from this first set, 1, 2, 3, 4, so on. From the second set, I'm going to add in 2, 3, 4, 5, and so on. And then from the third set, we're going to add 3, 4, 5, 6, and so on. But the thing to keep in mind here is that A2 is actually already contained as a subset of A1, because A1 has all of the positive integers. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, off to infinity. And all of these other ones that come after in the family start later. So here we start at 1, A2 starts at 2, and so on. So this one starts at 3, the next one will start at 4. But all of the positive numbers, positive integers, excuse me, are already in A1.
So would that make A3 a subset of A2?
Yes. Yeah. So A3 would be a subset
And
of
it
A2.
just continues.
A4 would be a subset of A3. Yeah, that's good.
As well as all the others in front of it too, right?
Right.
Okay.
So since all of
So A1 and A2 are like,
go ahead.
are A1 and A2 like different families inside of the set?
No. So A1 is just a set. The members of A, its elements are just numbers. So A1
Right.
is a set of
A1 is a
numbers.
whole set itself.
Right.
Okay.
Yeah. So this is kind of, it's a bit more complicated example, so that we can kind of stretch our imagination here. I have a family with an infinite number of sets in it, and each of these sets also has an infinite number of elements. So it's kind of a bit of a stretch compared to a little family like this one, where we can just write it. But if we add up all of the elements, we're really not adding anything when we go to the next one, because all of these other sets are already part of the first one. So the union of S is really just the positive integers, 1, 2, 3, 4, and so on. It's really just the first set. Okay, so let's stick with this family as we go to this next concept. So now we want to look at an intersection of a family. And it's the same kind of thing. The intersection of a family S is the intersection of all sets in the family S. And this is the set builder notation. The intersection of S is equal to the set of X, such that X is an element of big X for all sets big X in your family. So let's try to work our way through that to see what it means. So keep the same family. We're still looking at these sets of numbers. And let's see if we can think through what should be in the intersection. So what numbers are going to be in all of my sets? That's what I need to answer. In order to figure out the intersection of this family up here. So what numbers?
All integers.
Okay, so all integers. So let's just pick a number. 42 is a good number. So 42 is in my first set. It's going to be in my second set, my third set. Is the number 42 going to be in A50? No. And before I continue that thought, someone asked, will S always be the same? No. I'm just, for this example, I'm keeping my same family. When you go to your homework, you're going to see different families. So, okay, backtracking. 42 is not going to be in A50. So there's definitely one number. Can you think of any other number that would not be in at least one of these? Like what about 1,000? Is the number 1,000 going to be in all of my sets? AI? No, because if I go to A1001, it starts at 1001. So it doesn't have any of these other numbers before that. Okay. So what do you think? What will be in all of the sets?
AI. Or I.
So we have to be a little bit more concrete. If I just want to write out what numbers are in it. Someone in the comments said, would infinite be in all of them? Something, I guess, that hasn't come up yet this semester or in this class. Infinity isn't actually a number.
Is it the universal set?
The universal set, so the universal set would be everything. So that might be like all the numbers. But we definitely know that there are some numbers that aren't going to be here, like 1,000. So let me tell you what it is. It's nothing. The intersection is the empty set. Because if I pick any number at all, like the two that I did earlier, 42 and 1,000, if I go far enough along, if I go far enough down this list, there's going to eventually be some set where my number doesn't live. So even if I pick 500 billion, I can go far enough along in this list. I can go to 500 billion and one, and it won't be in that set. So the intersection is actually nothing. Okay, and in the last 2 minutes of class, let's talk about ordered pairs. So in mathematics, we call ordered pairs Cartesian products, or when we're talking about sets, we call these Cartesian products. This is a famous French mathematician, Descartes. Okay. So a Cartesian product of two sets, and I'm just going to call my two sets x and y, is the set of ordered pairs x comma y, where little x is in the first set and little y is in the second set. And the notation for this, if you want to talk about the set of ordered pairs, we write it like multiplication. X, big X with a little multiplication symbol in between, and then Y. And let's get a good concrete example here in the last minute. Let's look at two little sets. X is going to have 1 and 2. Y is going to have 1, 2, 3. And if I look at the Cartesian product of x and y, I want to find all the ordered pairs where the first thing in my ordered pair comes from x and the second one comes from y. So it's a set, and then I could have 1, and then I could have 1 from this set. Then I could have 1 for my first number, and then 2 for my second set. I could have 1 and 3. Okay. So that finishes off 1. I've already paired it up with everything over here. So I'll have to move on to 2. Right, 2, 2. And 2, 3. Those will work. But we should also add in 2, 1. Okay. So the thing about ordered pairs, the most important thing about ordered pairs is that their order matters. 2, 1 is different from 1, 2. This is different from how sets work. So if I was just talking about a set with 1 and 2 in it, that one and that one would be the same. But since they're ordered pairs, the order really does matter. So these two are different. Okay. Right, and that's it. Because we've paired up 1 and 2 with everything over here at this point. So there's 6 elements. And something that I want to point out is that if you multiply the number of elements in your first set with the number of elements in your second set, 2 times 3, you get the number of elements in the Cartesian product. So that's where this word comes from, the product. It's because the number of elements here really does come from multiplying these two numbers, taking their product. Okay, it looks like we need to stop there. So if there aren't any questions, you guys can go ahead and go. I'll stick around for a minute or two, and otherwise I'll see you guys on Wednesday.